Let's start our algorithm by analyzing the different libraries and data definitions that we need for this program. In the module section, as in previous implementations of cellular automata, we're going to need the Pygame library, but in this case, we are not going to need the random library. In the data definition section, we're going to start with the parameter dimensions. This is a compound data type of type tuple, which contains two integers, representing the number of columns and the number of rows that our grid is going to have. The next component is called resolution, or res, which represents the dimensions of each of the tiles, aka the bees. The next element, the screen, results from the multiplication of each of the elements inside of the tuple dimensions by the resolution to transform the number of columns and the number of rows into a total number of pixels per width and per height. The display is going to be the window, and it belongs to the class known as surface. To create it, we need to call the sublibrary display, which includes the method setMode, and to setMode, we're going to pass the tuple called the screen, which is represented by the pair of integers representing the width and the height. FPS represents the frames per second. In this case, we want to show the users 10 frames every second. In this particular case, we want the animation to be fast enough, but not too fast. If we set the standard in the field, that is 30 frames per second, then the animation is going to happen rather quickly. We'll demonstrate the differences on this parameter once we finish the implementation. Time be rest and time be active represent the amount of time that we're going to wait for the bee to replenish its energy, so to speak, before it can turn its state from 0 to 1 in the presence of a stimulus. The parameter time be active represents the timer that will indicate for how long the bee will keep its state 1 before going back to state 0. The data definition tile is the basic unit of information in this program. As in previous implementations in cellular automata, this class receives in its constructor the number of column and the number of row, which are later used to calculate the position in pixels of that particular tile in the game. We also have a state and a next state, which is a binary value, which contains a binary integer value that can be 0 for white and 1 for black. What is special about this algorithm is the fact that each of the tiles is going to contain a tracker for their own respective timers. They come in pairs. The first pair represents the time that the bee is going to stay in the state 1. We call it timer in state 1. The first attribute represents the actual counter. The next element, reset timer in state 1, will be used as a reference to set the value of the timer back to this constant right here, so that every step of the algorithm has the same duration in time. Recall timer and reset recall timer are the counterparts for the stage at which the bee is going to be resting and is not going to get active to change from state 0 to 1. Line 30 creates the rect component, which is the actual rendering of a square with the physical properties that allows us to evaluate collisions against this object named tile. The two helper functions that this tile contains are called draw and getColor. Draw uses the draw sublibrary rect method to render in the surface called display, which is the screen where we see our animation, a tile of dimensions given by self-rect with the color received as the return of the call to the function cell.getColor, which simply maps each of the binary states to one color. The grid is a two-dimensional structure represented by a list of lists. Like before, this grid is generated procedurally. That means that we use for loops to automatically generate entire columns, which is this for loop right here, and appending each tile that we create in each column at the position C and R given by the for loops, and then appending it to the row. That row is later appended to the grid. So a grid is a list of rows where each row is a list of tiles. That structure is reflected in the template for our grid. To traverse this two-dimensional array, you need to use a two-dimensional for loop system. A for loop nested inside another for loop. We're going to be using this template throughout the entire program. So this is one of the most important elements in our code. Let's start the coding section. The first thing we'll do is to create two functions called draw and update. This is the standard way by which we build programs using Pygame. The draw function is going to be in charge of rendering all the information that has to get visually represented in the screen. So we take the surface display and we called a color, in this case green, that is going to serve as a background. If our program is written properly and the tile system is built properly as well, we shouldn't be able to see any green at all, because every pixel in the grid should be displayed using the color that belongs to a particular tile. In other words, there is no overlapping and there is no gaps left in between the tiles. Remember this template for grid? This is the first time we're going to use it in the system. We're going to copy the template and we're going to paste it in line 61. We fix the indentations, get rid of the comments, and we are ready to use it. This template is used to traverse the two-dimensional grid. These three dots represent a particular action, a verb, which in the case of programming usually takes the shape of a function that receives as an argument this tile. But not all functions are global. This is to say that some functions belong to the particular objects we are dealing with. That's one of the beauties of object-oriented programming. So we're going to call the function draw, which we created as a helper function inside of our class tile. Afterwards, we're going to need to call for a handshake using the display sublibrary of the Pygame library and using flip. This communicates with the real programming language, I think is C, that actually renders an image and works asynchronously, because Python doesn't have that power. We're going to put a pin in the update function for now. To render our animation, we need to call an infinite loop. That is going to call draw and update. In the update function, we are going to ask first for an interactive window, and that is done using a for loop that iterates over every event in the list of events that Pygame gets. That is, every input that we may have done using the mouse or the keyboard, or even interacting with the window itself inside of our computers. So if the event is of type quit, we call pygame.quit, asking to finish the implementation. By doing this, we can run the program, and you'll notice that we have a white window. This window is in reality the visualization of our two-dimensional grid. It's just that there is no overlapping in between our tiles. That's why we don't see the green background. Next, we need to ask if the mouse is being clicked. To do this, we're going to use another if statement, and we're going to ask if the type of event is of type pygame.mouse button up. We're going to use mouse button up because the computer is way faster than we are. An event that we believe is just one click down, depending on the speed of the computer, may be taken as multiple clicks at once. But there is only one up event. It just gives us more control and prepares us to avoid any unexpected results. We need to extract the position where the mouse has been clicked. To do this, we're going to use the Pygame sublibrary call mouse, and we're gonna call for the action or method called getPosition. That is gonna give us a tuple that we are dividing in two variables called mx and my for mouse x and mouse y. Now we need to iterate over the template for grid. Once more, we copy the template and we paste it in line 72. We fix the indentations, get rid of the comments, and the action we need to implement is a question. We want to ask if the tile rect component, which is the hitbox of the square that we call the tile, is colliding against a point made out of mx and my. If the answer is yes, it means that the click has overlapped a tile, and we can therefore change the state to 1. Let's see if this works. Here we have again our white window. However, if I click, wherever I click with the mouse, the color of those tiles changes from white to black. Now that we have the input system ready, it's time to work on the implementation of our algorithm. We are gonna copy and paste the template for our grid again. For every single tile, the first thing we are gonna do is to create local variables R and C. The purpose of these local variables that are gonna be redefined for every tile in the entire grid has the purpose of making the process of counting the neighbors much easier. We're gonna create a list ns for the neighbors, and we're gonna start an array. Grid at index R and C is the tile of interest, which is this tile right here. To count all of the neighbors that are in the previous row, we need to say R minus 1. We need to change this R to R minus 1. Let's move to the next line. Let's copy this grid again. That's the row where the tile is, where the actual tile of interest is. And this last row is gonna be the row below where the tile of interest is. This would be the tile that we are focusing on right now. And that means that we don't need it here, because the purpose is to count its neighbors. But I'm just gonna leave a space in there. Now it's easier to see. This empty space is where the tile used to be, and all of these ones are its 8 neighbors. The second row has all of the elements R without addition or subtraction, because they are in the same line where the tile of interest is. But these ones are in the row below, which means +1. In Python, the y-axis is inverted. To add values, we go down, and to go up, we need to subtract values. If you have seen the video of Conway's Game of Life or Langton's AND, we have already talked about an issue that emerges at this step. Python automatically takes the values r-1 or c-1 to be the elements at the opposite side of the screen in the y and x axis respectively, when these elements are located in the edges. But for r+1, we receive an error that will say list index out of range. What we need to do to wrap the world around it so that the last elements at the right edge and bottom edge of our screen have as their neighbors the elements at the top and the left side of the screen, we need to use the modulo operator with dimensions at index 1. That is to say, if the index of the row +1 is bigger or equal than dimensions at index 1, which is 32, then we turn that value into 0, making the position equivalent to the first item in the list. We're almost done. See, here on the items on the left of the tile of interest will be -1. The ones in the middle are the item C, and the items at the end are going to be C plus 1. Here, we need to apply again the concept of modulo in order to create something known as a flat terrace. In this case, we're going to use dimension at index 0. Great. After counting the neighbors, it's time to apply the algorithm. If the tile state is 0, that's to say that the B has not been activated and is white, we need to ask if the sum of all of the states of the neighbors is bigger than 0. If the answer is yes, it means that there is at least one neighbor that is black, meaning that there is a stimulus coming our way, which means that we probably need to propagate that stimulus if we are not too tired as a B. We're going to ask if the sum of a list is bigger than 0. The problem here is that the list NS is not a list of integers. It's a list of compound data types of type class tile, which means that I can't extract the elements one by one unless I add the square brackets and call list comprehension. Here I can call n for neighbor, and I can call its state for every neighbor in the list NS. This is equivalent of mapping information, which is a higher order function. We're just turning one form of information into another by filtering the data that we need out of a compound data type called n. The syntax may throw some people off, but it's just a fancy way of writing for loops in one line. If the sum is bigger than 0 and the B is not too tired, we do this by asking if the recoil timer is less than 0. If the answer is yes to both questions, we can make the tile next state. Remember, we don't modify the current state directly because we still needed to calculate the states of the other tiles in the grid in this iteration. Then we can change the tile next state to 1. Otherwise, the tile.recoil timer is not equal to 0, but we need to make it closer to be 0. So we can subtract a constant parameter. Let's call it 0.1. This may be a hyperparameter, maybe a good idea to make it into a constant at the top. But for now, I'm just gonna keep it here. Something is wrong with my tabs. Let me check something. There we go. In VS Code, pressing Alt-Shift-F, in Python at least, with the standard add-ons, auto formats your code. So that is what happens if the tile state is 0. But otherwise, it means that the tile state is already 1. If the tile state is already 1, we need to ask if the timer that counts when the tile's state should change from 1 to 0 has reached the target of 0 or less than 0. So we ask if the tile's timer in state 1 is less than 0. It means that it's time to change the state. The B has gotten tired, it's time to get inactive. We are gonna first change the timers in state 1 to the reset value, of that parameter. And we do the same thing for the second timer, which is called recoil timer. Because now that the B has done its work, it deserves some rest. So we reset the amount of time that the B has to rest so that it can take a break. So we set tile.reset recoil timer. And finally, we set the tile next state to 0. But this is not the only possible outcome. If the timer in state 1 is not less than 0, it means that it's bigger than 0 or equal to 0. In that case, we simply make the value get smaller so that it gets to a point eventually in which it can exit the state 1. That's it. Now, the last thing we need to do is to iterate over the entire two-dimensional array that we call the grid once more. And we're gonna do it after we finish with all of that. We're gonna copy the template for the grid one last time, and we're gonna paste it here. We fix the tabulations, get rid of the comments, and we are ready to proceed. The only thing we're gonna do here is to change the state of the tile to be the tile next state, making therefore the next state the current state. If our program is well written, we should have a waving behavior. Oops, we got an error. And it says tile object has no attribute next state. I can see it here in my console. I may need to pause this. Oh, I think I found the problem. The console says that there is no attribute reset recall timer. It seems that the error connected to the lack of a next state attribute were some old messages that I had in the terminal. So the name of the parameter is reset recall timer, but it uses lowercase r rather than changing it down there. I'm going to change it here to capital R, and let's see if that fixes the problem. And yes, it does. Now, I don't know if you noticed this, but we never use frames per second. Again, this is an issue that I usually struggle with. I just forget to change the frames per second, but you can see what the effects are. The program is extremely fast. If these were bees, you would probably have some health issues from looking at those bees for extended periods of time. Okay, so let's use the frames per second. And to do that, we just need to go to the draw function, the global draw function right here. So here we call the Pygame library, the time sub library, and inside there is a class from which we can instantiate a timer, which is called clock. The clock has a method called tick, and here we can call FPS. Let's run this again, and let's see if it works. I click somewhere in the window, and you can see the accumulated effect of the waving behavior.